Good morning, students. In the 4 levels of abstraction, we have studied about the gate level abstraction for modeling any hardware circuit. Now let us discuss about the data flow abstraction level. For the smaller circuits, the gate level modeling approaches works very fantastic because the number of logical gates that are to be connected for realizing our circuit is very limited, as a designer can instantiate and connect each and every logic gate individually with the help of wires. But sometimes what happens, the complicated and sophisticated designs may have a very large and enormous number of gates, where the hardware designer feels some tidiness in connecting and picking each and every logical gate to achieve the required functionality. That is, the designer now it is the stage where the designer can design more effectively if they concentrate on implementing the functionality of the design at a level of abstraction that is higher to the gate level abstraction. Now this, like you can see in the figure, so I am having here 3 logical gates. Now the designer can develop he can model this hardware circuit by using Verilog HDL using gate level abstraction. So he feels very comfortable at this stage. Now moving to the second diagram, you can see here as the number of logical gates are increased. So when compared to the earlier designing process, now he felt some uneasiness because the large number of logical gates are there and more number of interconnections are also have to be designed and connected among the gates. Now if still the number of gates are increasing, so the same happiness the designer may not face, like you can see here, because he will be getting shocked as I can able to find a plenty and large number of primitive gates or logical gates, and they have to be connected by using the wires. So he feels some cumbersome process, okay, and heavy process it is. So now it is the time for data flow abstraction. So what is this data flow abstraction? That is, Verilog HDL allows a circuit to be designed in terms of a data flow between the registers. Okay, so like between the register, this is the register, this is the register, and how the data is processed in the circuit. Okay, that is, I can able to define that Verilog it is allowing us to design a circuit in terms of the data flow between the registers and how your design is processing the data rather than instantiating or picking or collecting or arranging a large number of logical gates. You can see here. So how the design is getting processed, that is the main important, instead of picking and connecting the logical gate to achieve the functionality. So here we are following how the data is flowing between the registers, a logic we are developing here. Okay, so we know that the gate density on chips are day by day increasing rapidly. So it is a best practice to use a data flow modeling. And one more thing here is, we do also have in our VLSI design flow automated tools like logical synthesizer are there. So whatever the description of your circuit which is written in the RTL, that is register transfer level, is nothing but here at the RTL whatever we are using here is developed by using data flow modeling is converted into the gate level circuit, who is converting the automated tool, that is logical synthesizer. What it is doing here, its job is to convert the data flow hardware description language into the gate level circuit. Okay, so now let us see here some of the points. So like data flow modeling, mainly we will be developing our HDL or RTL description. We employ assign as a keyword, ASSIGN. So this, whenever in the program of RTL if you find assign, so it is nothing but we are using data flow abstraction. Okay, so so here what is happening, I am having like for example, let me take this as an example. And gate is there, so module and, so let me keep the module name as and one, and the outputs and inputs are, output is out, this is my output variable, inputs are a comma p are the input variables. So exclusively I'm defining what are the inputs and output variables and its type. Okay, so what is the logic here? I am doing AND operation. So assign out, that is output is output variable equal to a, and operator, this is and b, end module, that's it. So here LHS, it is out, this is the output variable called out, its data type should be of type wire. And RHS, this a and b, these input variables, it may be of type register or it may be of type net data types. Okay, so let us move back here. So as discussed, data flow, a continuous assignment. So data flow modeling uses a continuous assignment statement with a keyword assign. So I am using here assign, and this is my continuous assignment. Okay, so this continuous assignment is a statement that assigns a value to a net. What is the net here? A net is nothing but the output variable. For this output variable, continuously something is always assigned. Okay, the value assigned to the net is specified by an expression. So in this example, if out is my net, the value assigned to this net is specified by this expression, because variable 1 and variable 2, of course these are the operands separated by an operator which results me an expression. Okay, so the value assigned to the net is specified by an expression that uses operands and operators like this. Now the data flow modeling uses a many number of operators that act on operands to produce the desired result. So what is the result I require here? I want and result. That means two signals are there, and these signals are sent to as an inputs for my AND gate, and what will be my output, that is OUT. Now let us see, let us have some differentiate, like how your gate level abstraction design and data flow abstraction level design are different according to the programming technique. We will see now. So I am having a module, this is my 4x1 multiplexer module, which is designed in terms of a primitive gates. Okay, now so if I want to develop my 4x1 multiplexer, I required here 4 number of AND gates, 1 OR gate and 2 inverters. Module, what is the module name? I have kept here mux421 and declaring all the inputs and outputs. So here in the argument itself only I am declaring the input ports I0, I1, I2, I3, S1, S0, as well as the output port, that is OUT. This kind of declaration is called ANSI style, that is ANSCII, ANSI style of declaration. Okay, and so once it is declared, the argument list, like, and its type, the variables and its type are declared in the argument list itself only. So we no need to define again exclusively in the under the module definition all the input and output variables. So in between I do have here enormous number of wires that is connecting one logical gate to other logical gate. So those wires are Y0, Y1, Y2 and Y3. Here also I am having S1N, S0N. These are nothing but the output of your inverters. So all these are nothing but the wires. So again, what are these variables? These variables are of type wires, because they are connecting one component to other component. So let us move, as we know how to develop or design a gate level modeling using this using this previous knowledge. So we are going to construct the design not. So this is my not two not primitives. I am having two primitive gates, not and not, s1 n, because this is the output of first not gate, this is the output of second not gate, and the input of your first not gate is s1, and the input of your first not gate is s0, like this. So as per the previous knowledge, you can able to recollect how I have written these instructions for modeling my 4x1 multiplexer in gate level abstraction design. Okay, and end module. So here, how many number of lines I have used? 1 2 3 4 5 6 7 8. Okay, so if the same design, if I want to develop in data flow abstraction, how can I able to develop? Let us see. So same, the module and with sensitivity list or the arguments, module name and its arguments. Simply I have used it here one line. You of course you can able to find here 4 lines, but it's not 4 line, it is simply a one line. How? Assign out, because this is my output variable, out equal to. So what is happening for this AND gate? This is second AND gate, third, fourth. These 4 AND gates are passed to your OR gate. So OR gate inputs are what? Y0, Y1, Y2 and Y3. So that means here OR gate is performing OR operation, AND gate is performing AND operation. So OR gate is performing OR operation means I need to use OR symbol or operator. You can see here, this one vertical line, this is my OR operation. So what is this one? This is nothing but Y0. So how this Y0 is obtained? So let us move back to this one. Y0 is the output of your AND gate. That means the input for your AND gate is I0. S1, it is passed to an inverter. We have got here S1N. S0 we have passed to inverter. We got S0N. So that means, can I write as negation S1, negation S0, as well as I0? These three are acting as input for your AND gate. That means if these three are acting as input for your AND gate, means can I separate these three variables or three operands by using ampersand or AND operator, like negation S1 and negation S0 and I0? I have finally realized why not. In the similar manner, I can able to develop y1, y2 and y3. So once I have got all the outputs of my AND gate, these are passed to as an input for my OR gate. So OR gate, if I am passing any signal to OR gate, means definitely OR operation have to undergo. So all these y0, y1, y2, y3 are undergoing the OR operation, like this. So the purpose of using the data flow abstraction here is, I don't have any requirement to define the intermediate variables or wires here. I am just directly using what is happening, what is the logic that is happening in the circuit, because I didn't picked or I didn't instantiated any primitive gate here, and connections I didn't established any connections in between the gates. I just have written the logic. So this is the way or the advantage why we are going to use data flow modeling. Okay, now let us see next one. So in this way you can develop all the basic gates. So if the inputs are a comma b, outputs are and1 or 1 not for something. So and means it is ampersand, or if the output is OR gate, OR1 is A or B. This is the OR operator. NAND is, first we need to perform AND operation, after that negation. For NOT, first we need to perform the OR operation and negation. In this manner we can use the data flow abstraction. So this is one more thing, module half adder. How to design a half adder module in data flow abstraction? So half adder is consisting of what? One XOR gate, one AND gate. So that means instead of picking and establishing the connections, what I am doing here, I just have written two instructions. That is for sum. That means output is realized in terms of inputs. Sum is nothing but a XOR b assign carry equal to a ampersand b. So here, what I am doing here, I am not instantiating and connecting every gate. I am just writing the logic, how the data is flowing between inputs to outputs. That's it I am concentrating. Okay. So this is one more thing. This is a simple example. Assign. This is my output variable. Module name is and1. Assign out equal to a and b. So what are these? What do you say? It is a continuous assignments. So the continuous assignments are the most basic statements here in our data flow modeling. These continuous assignment statements are used to drive a value on to a net, because in the previous example I have said you this is my output variable out. This out is of type wire or it is of type net. That means the continuous assignments are here used to drive a value on to a net. So this continuous assignment is this equal to, it is equal to is driving a value onto this output variable out. So from this expression I am getting some value, this is being given to my output out net. Okay, so this assignment replaces the gates in the description of the circuit. Like are you able to find out any primitive gates in the definition of the module? Nowhere you can able to find out. So here the description of the circuit is a higher level than the gate level. That means we are using here data flow abstraction by using the keyword assign. So this is the thing you need to remember. Okay. Now we do have some characteristics whenever we are using the continuous assignment. That means some standards we need to follow. That is the left hand side, like assign something equal to something. So the left hand side, this part, the left hand side of an assignment operator must always be a scalar, or it may be a vector, net, or a concatenation of a scalar or vector nets. So Cout is what? It is a scalar. Sum 3 down to 0. It is a vector. So must always be a scalar or vector or a concatenation of scalar and vector. That means I am clubbing a scalar and vector. But the left hand side should definitely be of net or wire data type. So assign Cout comma sum 3 down to 0 equal to a 3 down to 0 plus b 3 down to 0 plus cin. So this combining a scalar and a vector or a many number of scalars or a many number of vectors, a combining is nothing but concatenating. We use the word as concatenation. So as this is this equation or this instruction is performing the definition for 1 bit full adder. Next, so we do have the second rule. Continuous assignment statements are always active statements. Why? Because the assignment expression, because this is my expression, and of course this expression is being assigned to someone, is evaluated as soon as one of the RHS I1 or I2 operands, which are nothing but the operands, changes. So like for example I1, if for this one I have taken as 1 and I2 if I taken as 1, so 1 and 1, the output is 1. If I1 value is changed to 0 and I2 remains the same as 1, so 0 and 1, the combination is, the output is evaluated as 0. So the assignment expression is evaluated as soon as one of the right hand side operands changes and the value is assigned definitely to your output variable called OUT. This is the second character. And the third character is the operands on the RHS. That means this one. It may be of type reg, or it may be of type wire, or something else like, or it may be of vector select or path select of a vector, something else like that. Like you can see assign. So we are using here equality operator. Wherever we are using equality, we have to definitely use the assign operator. It is a keyword. Okay, assign is a keyword. So assign address 15 down to 0 equal to address 1 bits 15 down to 0 xlog exclusive or address 2 bits 15 down to 0. So this is of type vectors, and this is also a vector quantity. So in this way we can do. Again, these continuous assignment statements are again classified in some category. So what are them? What are them? We see, like we have seen here. Yes, let's move. So let us take the same example, and one. This is A and B are the inputs. Out is output. So the RH, this output variable definitely have to be of type wire or net. Input may be a scalar, or it may be a, sorry, it may be a what do you say, a register, or it may be a wire data type. So what's happening in the implicit continuous assignment? Instead of declaring a net and then writing a continuous assignment on the net, so Verilog provides where a continuous assignment can be replaced on a net whenever it is declared. So what is happening according to the definition? Instead of declaring a net, that means out is declared here as a net, that is of type wire, and then writing a continuous assignment on the net. So once out is declared as a wire, and in the next instruction I am writing the continuous assignment out equal to A and B. This is my continuous assignment. This value is assigned to here. That is continuous assignment. So this is a normal or the regular style as discussed previously. So instead of this one, we do have one more style of declaring this assignment, of performing this assignment operation. That is, Verilog provides by which a continuous assignment can be placed on a net whenever it is declared. So as soon as I have declared out as of type wire, immediately what I am doing, a continuous assignment, immediately I am assigning or placing onto the net. That means I am not using here assign keyword. That is the difference you need to observe. So because as soon as out is declared as a wire or net, immediately a continuous assignment is placed on my out variable. This is a continuous, as implicit continuous assignment. And the next one is, so sometimes what happens, if a signal name is used to the left of the continuous assignment, okay, like left of, this is my continuous assignment, this is my signal name, that is out, okay, an implicit net declaration will be there and provided by the simulator. Why? Because here a comma b I am defining as of type wire, but I did not mention what is out. This out, it is of data type reg or it is of type net, I didn't mention. So who will take care of that? Simulator will take care of that. That means if a signal name is used to the left of the continuous assignment and I didn't provided its type, an implicit net declaration will be inferred. So here A and B are of type wire or net. So simulator will give that out, and that means simulator will declare implicitly that out it is of type wire data type. Okay, so implicit wire declaration for out is done by the simulator. This is what happening. Okay, this is one kind of continuous assignment declarations. Okay, so far we have gained about continuous assignments, but at some or the other point practically any logical gate or any functional circuit will definitely undergo some delay. As like if you are inserting an inputs now, immediately you will never be getting the outputs. So definitely a delay is present for any logical circuit realizations. So how the Verilog is going to provide you like what is the impact and how can you define or how can you apply a delay in a program, we will discuss now. As the delay values control the time between the changes in the RHS expression and when the new value is assigned to the left hand side. Okay, so we will take the same example, assign #10 out equal to a and b. So here a and b are the inputs, out equal to a and b. So if I have sent 1 and 0, output should be 0. But in practical circuit, if this AND gate is having a delay of 10 seconds, that means after 10 seconds output will be getting the value of 0, like this. So I am having, okay, yes, I will explain you this one. Okay, so this kind of the delay is represented using the what do you call this? This is one hash symbol. A number followed by hash shows the delay value. So this hash a number. Okay, so this one represents a delay. So this here we can able to see that the delay is present to the left hand side of your assignment operator. We call it as an inter assignment delay, and if the delay is present right side of your assignment operator, we call it as an intra assignment delay. Okay, let us discuss this one in brief. So the format for specifying any delay is assign hash, that means delay net, because LHS should be of type data type net equal to expression. RHS, it may be an expression or it may be of scalar or a register or a vector data type. So assign sum equal to a exclusive or b, because it is a no delay here you can find. If a exclusive or b operation is performed and as soon as the value is evaluated, the is evaluated to output, but in this one the sum will be receiving or will be displaying the evaluated value of a exclusive or b expression after 2 time units. This hash 2 indicates 2 time units, because every time I am saying 2 seconds or 2 nanoseconds, it is always advisable to mention or to use as time units. So if no delay is specified here, it is no delay, that means defaulted. That means as soon as inputs are given, output is evaluated. So what is this time scale? That means time unit we are using here. So what is this time unit actually? So associate time unit with physical time. So whenever I am starting any Verilog HDL program, like time scale, I discussed this point in my previous session on ripple carry counter. Like I have demonstrated how to execute the ripple carry counter, right? At a time I mentioned a point like tick time scale 1 nanosecond per 100 picosecond and what are its impact in the waveform window or the simulation output window. So tick time scale 1 nanosecond or 100 picosecond. So I am having here time unit as 1 nanosecond, and this is my precision. Time precision is how much? 100 picoseconds, that is 0.1 nanosecond. So if I am having the practical time or the physical time as 10.512 nanoseconds, it is taken as 10.5 nanoseconds only. There is a separate topic on this timescale compiler directive. I will explain you in detail at that time. Meanwhile, you just notice if I am having assign hash to sum equal to a exclusive or b. So hash 2 is nothing but 2 time units. So what is the time unit here? 2 time, if here 1 nanosecond by 100 picosecond, that means 2 time units, 2 nanoseconds. If I am having 50 times 50 hash 50, it is 50 nanoseconds. If I am having hash 20, it is 20 nanoseconds, like that. So I have taken an example here. Take time scale 1 nanosecond. What is the time unit? 1 nanosecond. So A exclusive or B is assigned to output sum. So that means immediately, immediately as soon as A and B receive the values, output we are not going to get. The sum have to wait for certain time unit, that is 3 time units, 3 nanoseconds it is waiting. Similarly, A and B, carry is waiting for 6 nanoseconds. So you can see here, A is changing its logic at 9 nanoseconds and it will be logic 1 up to 18 nanoseconds. Similarly, B is, at 9 to 18 nanoseconds, A is 1, B is 0. So sum, what is the sum here? 9 plus 3, that is how much? Okay, so yeah, from here to here we'll see 0 nanoseconds. This is 0 nanoseconds and this is my 9 nanoseconds. Okay, so this 0 and exclusive or 0. So 0 and exclusive or 0 is, of course, it is 0 or 1. Okay, I have taken some wrong here. It should be inverted, 0 and 0, because it is shifting here 3 nanoseconds. It should be logic 0 only here. I will explain with one more figure. Yeah, this is good. So I am having here A value from 0 to 10 and B value from 0 to 10. It is both are logic zeros. So output is uncertain, I don't know. Okay, so 0 and 0, from 0 to 10 it is 0 and from 0 to 10 B is also 0. So from 0 to 10 seconds, let me take the time unit as in 1 second. Okay, so from 0 to 10 output is uncertain. Why? Because output is waiting, it have to wait for 10 seconds to present or to display the value. A and B, this expression is giving some value to output variable out, but output is not displaying the result of A and B because it is waiting for, because it is consuming, the circuit is consuming certain amount of delay, that is 10 seconds. After 10 seconds the value will be expressed as an output. So 0 and 0 combination is 0 here. From 10 to 20, A is 0, B is 0. So the output will be present from 20 to 30 for A and B inputs for 10 to 20 seconds. The output will be exhibited after 20 to 30 seconds, during 20 to 30 seconds. That means for any changes of your input variables, the output will be presented or displayed after 10 time units, like this. 1 and 1. Here you won't get 1 here. Why? Because it have to wait for 10 more seconds. After 10 seconds, like at 20 seconds, A and B are having a value of logic 1. At 20 seconds, you will not be having out a logic 1 because out have to wait for 30 seconds, and after 30 seconds, it will be displaying you as logic 1. So this is the impact of delay. Now, so what is this regular assignment delay? That is, any changes in values of A and B will result in a delay of 10 time units. Okay, you can are able to observe, and time units, and the expression A and B and the result will be obtained to OUT. Okay, as discussed. So you can once again I am redefining you. I am having a signals A and B, and these go high at 20 seconds and out goes to high after 10 time units, that is in fact 30 seconds. Okay, this is what happening here. Okay, next, what is this implicit continuous assignment delay? as discussed with what is the implicit continuous assignment and implicit net declaration, these are without any delays. If a delay is inserted, so that is accordingly we call it as an implicit continuous assignment delay, and we call it as a net declaration delay. Okay, so this is used to implicit continuous assignment is used to specify both a delay and an assignment on the net. A delay as well as an assignment and on the net. As soon as out is declared as an of type net, assignment is being declared and also delay also being declared. This is about implicit continuous assignment. So what is this net declaration delay is? A delay can be specified on a net, okay, when it is declared, okay, then any value changes applied to the net out is delayed accordingly. Okay, so here only I am declaring the output variable, or whenever I am declaring this of out is of type wire, at that time only I am declaring here a delay for that. Next, what the expression assignment is, the assignment is assigned, the result of this expression is assigned to out, but the out is priorly declared with #10 as its delay. The output variable or the output wire is priorly having a delay of 10 time units. So this is the difference. Okay, this is about continuous assignments and delays. Next is one more important topic in our data flow modeling is expressions, operands and operators. So without these things we cannot able to develop any Verilog HDL in data flow abstraction level. So what are the expressions? So these expressions are nothing but expressions are the constructs we call sometimes. So these combine mainly operands and operators to achieve some desired result. As we know that the data flow describes the design in terms of expressions, instead of using the primitive gates and connecting them, all the things are defined in terms of expressions, operators and operands kind of things. So you can see here example, assign C equal to A exclusive OR B, and assign this kind of thing, and this is OR operation. So this is an expression, the right hand side is purely an expression. This expression is nothing but a combination of operands and operator. Next is operands. So what is this operand? Operands are nothing but these are the variables. It can also be a constants or an integers, or it is of real numbers, nets, register, or whatever it is, data types, whatever it is. Okay. So I have here count comma final count as a variables. These variables, it may be an input or output or in between, I don't know, in a circuit, but it is of type integer. That means we call it as an integer operand. Here A comma B comma C, these are the real operands. Okay, these are variables or operands, because once these variables are defined or declared in terms of some data type, we call them it as a real operands. And this is a path select operand function type. So I will discuss what is this function type in the topic of task and functions. So that's it about operands, and let us move back to operators. So as in our any programming language, we do use the operators, which may be of arithmetic, logical, relational, equality, bitwise kind of thing. So in our Verilog HDL also we discuss in detail each and every operator briefly. So arithmetic operators we do have two types, mainly binary and unary. So what are the binary? Let me take A and B. These are type vectors because it is not a scalar in fact, and this is of a register vectors, and D and E and F are some kind of integers. So if I want to perform multiplication, I am using this operator A into B. It evaluates to like it is nothing but decimal 3, it is nothing but decimal 4. 3 into 4 is 4. So let me obtain the result also in binary format. This is multiplication, this is division. This is what d by e. D is 6, e is 4. Of course I will be getting in some fractional part. We are ignoring here the fractional part, removing the fractional part, and quotient will be obtained here, evaluated to 1. And a plus b, that means we are simply adding the two operands, register operands. B minus a and e explode, e star star double star are there, means it is treated as a power, e to the power of f, that is 4 power 2, 16. Sometimes what happens, I may have an unknown bits in my vector, because vector is nothing but a combination of many number of bits. Some or the other time I may have to encounter with an unknown values like x, which is indicated with x, like p equal to 4-bit binary 1101 and q equal to 4-bit binary 1x10. At the time I cannot able to predict what will be the exact result of my sum. So sum will be evaluated to some again an unknown term, that is 4-bit binary xx, some kind of thing. So this is what we encounter whenever a unknown value is present as bits. And the next one is 13 percentile tree. So this percentile indicates it is a modulus. Okay, so 13%, you are aware of how to perform the modulus. Okay, 13 percentile 3 and 16 percentile 4, it evaluates to 0, and minus 7 percentile 2. So percentile is nothing but generally it is a remainder. So in minus 7 percentile 2, the remainder will be 1. Of course, whatever the sign is there by the divider, that have to be present here. So minus is there, minus, plus is there, plus. Okay, because 7 percentile minus 2 is there, you shouldn't evaluate as minus 1. It have to be strictly follow the 7 percentile 2, that means 7. Okay, dividend takes the sign of the first operand, because this is my first operand. Operand may be of type integer, or it may be a constant, or it may be a number, as I have discussed. So here the first operand is this one, and percentile is an operator, that's it. Next is unary operators. So what are the unary operators here? Plus and minus are acting here as an unary operator. These are used to specify if the number or the operand is a positive sign or it is having a negative sign, that's it. So minus 4 indicates it's a negative 4, and positive 5 is positive, plus 5. And this unary operator are having the highest precedency, that means highest hierarchy in among all the operators. We will discuss this one with an example afterwards. Moving to next operators, we are having here logical and relational. So what are the logical and relational operators is logical. So A have taken a register, it may be an integer or whatever a data type, A equal to 3 and B equal to 0. So whenever I am saying a logical operator, it always evaluates to a 1-bit value, which may be a 0 or which may be a 1, or sometimes an unknown value. Okay, so that means here what happening, if an operand is not equal to 0, definitely it must be a 1. If an operand is not equal to 1, definitely it might be a 0. This is the thing what we need to focus. Like logical and B. So 2 times I am using here AND operator. That 2 times I am using the symbol of AND means it is treated as a logical operator is performed here. So A double ampersand B evaluates to 0. That means here we are performing, of course, AND operation. So 3 and 0, but it have to evaluate to a 1 bit value, that is 0, because B I have here 0. And next is A OR operation, logical OR operation B, so it evaluates to logic 1. And A equal to 3, that means it is a true condition. So negation of a true condition, true value, negation of a true is false, it evaluates to 0. And B equal to 0, that means it is a false, negation of false, it evaluates to logic 1. So sometimes unknown may be also present. A equal to 2 bit binary 0x and B equal to 2 bit binary 10. So if unknown are present, the output is evaluated to x again. So sometimes I may have logical operation in between this kind of thing, like expressions. We call this one as an expression. If expressions evaluate to 1, if both a equal to 2 and b equal to 3 are true, that means if this is a true condition and this is also a true condition, that means it is evaluating to 1. Okay, evaluate, and if this is false and if it is true condition, it evaluates to a 0, that is false. So this is about logical operation. That means simply you need to remember the output may be a 0, or it may be a logic 1, or it may be a logic x. And the next one is relational operations. So I am having a equal to 4, b equal to 3, x equal to something, b, y and z. So a is less than or equal to, so this is also giving me only a logic 0 or a logic 1 as an evaluated product. Okay, so and also apart from logic 0 and logic 1, it also evaluates to x, because if any of your operand is having an unknown values in its quantity, it evaluates to an x. So this one is less than or equal to b. A and b, no, b is a greater one. Is this true? Wrong. So here a is a greater one and b is the lesser one, so it evaluates to logic 0. A is greater than b, right? Y is greater than or equal to x. Yes, it is also right. And y is less than z. Z, I don't know what is that, because it is an unknown, so I cannot able to predict the output. So these are about logical and relational operators. So so moving to the next one, equality operator. So what are these equality operator? These equality operators are, it may be a logical equality or it may be case equalities. So logical equality is indicated with 2 equality symbols, and case equality is with 3 equal assignment symbols, assignment operators. So logical inequality means inequality, that means we are going to use a negation, a not, okay, not equal, unequal, case inequality, not, and 2 assignment operators we have to follow. So here the main thing we need to be getting astonished is logical equality operators will yield an x if either of your operand has x or z, in its bits. Like logical equality I'm talking about, let me talk. A double equal to b, a is a true, b is also a true. It is of course true and true, it is a logic. Of course a equal to 4 and b equal to 3, both are trues. Trues means it is of logic 1 state, but logic equality, are they logically equal? Is 4 equal to 3? Never it is not equal, so results in logic 0. And x is not equal to y, x is 4 bit binary 1010, y is 4 bit binary 1101. Is these two are not equal? Yes, of course these two are not equal, that is why it is resulting in a logic 1. And x equal to z, this is my x and this is my z, are these two equal? No, because I am having one of the operand is unknown, so that is why it results in x. What I could able to define you is the logical equality operators, it may yield an x if the operand has x or z in its bits. Okay. So here what is the case equality means. So I need to use three assignment operators. Z triple equal to M. The case equality operator, it do compare both operands bit by bit and compare all the bits including x and z. So it evaluates either 1 or it evaluates either 0, but it not evaluate x as you found in logical equality operation. So individual bits also it do matches. Z equal to M. Z is this one, XXZ. M is XXZ, 1XS. Right, each and every bit are matching. So it results in logic 1. Z triple equal to M. Z is this one and N is this one. So the LSB here I have Z, the LSB here I am having X. So these two are not equal. So it results in logic 0. M is not equal to N. M is not case equality with N. M is this one, N is this one. Yes, it is not equal. That means it is results in logic 1. So here overall comparison. Here what happened, bit by bit comparison. So in the case equality bit by bit comparison, that is why it is yielding logic 1 or logic 0 as an output. Here it is an overall comparison. Okay, that is why it may yield a logic 0 or a logic 1 or a logic X as an output. So this is about relational and equality operator. Once again, just like a review. Greater than, we use this symbol. Less than, greater, symbols and the English words for the corresponding operations. Only case equality results returns 0 or 1 as an output. So next topic is bitwise operator. So what is this bitwise operator? We will discuss in the next session.